Yeah. So where did we leave off in the last lecture? So HMM state segmentation, Yuntov has it right. Okay. So here was our problem, right? We were talking of processes of this kind, like our problem of the arrow and the wind velocity. The aim here was to measure wind velocity using a noisy wind speed sensor arrows shot at a target. And the situation was that the wind velocity changes according to some functional process. And in our example, the wind velocity at any time was the same as the velocity at the previous time plus some noise whose statistics we knew. And the arrow position at any time depended linearly on the wind velocity and could also be modified by some noise, the accuracy with which you shot. And the challenge we said was given a sequence of observations, y, we had to estimate the current wind speed st. So, and maybe even predict things into the future. So this was an example of a process of this kind. It was a series data with trends, but this was specifically data of a kind where you had two levels of stochastic processes. First, you had an underlying process that seemingly randomly changed the wind velocity in our example. And then you had a second level process, which was also a random process, the position of the arrow. But the random process had as its function the expected value, the output of the first random process. So this was a doubly stochastic process, where one random process generated a state variable x according to some time series distribution, and a second level process generated observations as a function of the state of x. And I had presented a very simple toy example for this kind of process in the last class. Anybody remember what it was? Do you remember the example? The toy example, guys? The flying spider? No, that was not an HMM, was it? I had a different one. The kidnapping example, right? Exactly. So this is what an HMM is. It's a probabilistic function of a Markov chain. It models a dynamical system. The model states that the system itself goes through a number of states following a Markov chain model. On arriving at any state, it generates an observation according to a state-specific probability distribution. And so the way it generated an observation sequence was as follows. If you had a hidden Markov model process for a system like this one, then in this example, the underlying Markov chain has 4 possible states whose allowed transitions are shown by the figure here. Associated with each state was an observation distribution. The system progressed through a sequence of states following this Markov chain. Anytime it arrived at a state, it generated an observation from the distribution associated with that state, and so resulted in a sequence of observations. So the HMM here has 3 sets of parameters. First is the topology, of course, how many states and how many transitions. So in this example, we have 3 states, and the allowed transitions are shown by the arrows. The next was a transition probability matrix, which said what are the probabilities of transiting from each of the states to other states. So here, for example, the first row represents transitions from the red state. The second row represents transitions from the blue state. The third row represents transitions from the green state. And so when you're in the red state, You can transit back to the red state with probability 0.6, or go move to the blue state with probability 0.4. If you're in blue, you can transition back into blue with probability 0.7, or go to the green with probability 0.3, but there's no way of going back to the red state. So the probability of transitioning to the red state is 0. If you're in the green state, you have a probability of 0.5 of going to the red state. You have no probability of going to the blue state, so this is 0, and a probability of 0.5 of returning to the green state. So the set of all transition probabilities can be represented as a matrix. There's also a probability, generally represented by the symbol pi, of beginning the entire generation process in any given state Si. And then, of course, you have the state output distributions, one associated with every state. So for an HMM of this kind, we identified 3 basic problems. The first is that of computing the probability that it will generate a specific observation sequence. The second one was, given an observation sequence, how do we determine which observation was generated from what state? Meaning, given the observation sequence, we had to identify the underlying state sequence. And the third was, how do you learn the HMM parameters themselves from observation sequences? So for the first one, again, this is just a quick recap. We first identified a structure called the trellis. The trellis represented all possible state sequences that the HMM could have followed in generating any observation sequence. So the horizontal axis here is time. The vertical axis represents the states of the HMM. And each arrow here represents a valid transition. So these arrows, horizontal arrows, represent the event of transitioning from this first state back to the first state at each time. These arrows over here represent the event of transitioning from the first state to the second state at the next time, and so on. And so we saw in the last class that this trellis can represent every possible state sequence. Each node in the graph from this trellis represents the event of being in this corresponding state and generating the corresponding observation. So each node has a time index and a state index and represents the event of observing or generating that particular observation from that time index while being in the state represented by the state index. Now, in this trellis representation, if any given path through this graph represents a valid state sequence. And now, if you consider the subgraph that started at the beginning and ended in a particular node, this graph represents all possible state sequences that could be followed that end at this particular state S while generating the observation sequence. And so we associated a probability with this subgraph, which is the probability that the process will generate observations O1 through OT and end up in state S at time t. And we call this the forward probability alpha ST. So alpha ST at any node is the probability of generating all observations until time t and arriving at state S at time t. So is all of this familiar to you guys? Do you remember this stuff? Yes, no? What about the rest of you? Yes or no? I have one yes. Can I see a few more, please? Okay, thank you. And so we saw that this alpha could be recursively computed, right? So what was the recursive formula for alpha ST? Anybody remember? What was it? Anyone?
Is it like the previous alpha times the transition probability times the observation probability at that state?
Correct. So it was just this. You could arrive at any state from one of its parents. And so the alpha ST over here was the sum over all parents of the alpha for the parent times the probability of transitioning from the parent to the current state times the probability of generating the kth observation from the state. You can actually pull this P of x given S outside the summation. So this was the recursive formula for computing alphas. And so you could start off by computing the alphas at the first time instant, use it to compute alphas at the second time instant, and so on, until you computed alphas for the entire trellis. And then if you sum the alphas at the final time instant, then that's going to give you the probability of the entire observation sequence itself, because at the final time instant, you must be in one of these states. So if you just sum over all states, you just get the probability of the observation sequence itself. Right? Everybody remember this? Please say yes or no. Okay, thank you. So the second problem we looked at was state segmentation. You're given only a sequence of observations. How do you determine which sequence of states was followed in producing the observation sequence? So for this, again, the problem was this: you were given these observations, this observation sequence. You had to estimate the most likely state sequence that the process might have followed in generating this observation sequence. And for this too, we had specified a dynamic programming algorithm, which is based on this very simple principle, that if you consider if I define the best path to any state in any node in the trellis as the most likely path to that node, then the most likely state sequence through the trellis is going to be the most likely overall path from a state in the very first time instant to the state in the very last time instant. And now, so if I define the best path to any state as basically the best path through the trellis to that state, the most likely path through the trellis to that state, then we know that the most likely path to any state must be an extension of the most likely paths to its parent states. So to find out the most likely path to the state, you just have to find out which of these parents, when extended, gave you the overall most likely path to the state. So you would compare the probability of the most likely path to this state times this transition probability with the probability of the most likely path to this state times this transition probability to the probability of the most likely path to this state times this transition probability, and pick whichever was highest. And to that, you would then, so that would give you the identity of the parent on the most likely path to the state. It would also give you, if you multiply the probability of the most likely path to the best parent with the transition probability, and then subsequently with the probability of the observation at that time itself, then that's also going to give you the probability of the most likely path to the state. So using this very simple logic, so again, you could start off at the first time instant. At the first time instant, the most likely path to any state is just the state itself. And the probability of the most likely path is simply the probability, the initial probability of the state times the probability of the observation from that state. From that set of probabilities, you could go to the trellis nodes at the next time step. And for each node, you could find the best parent and keep track of which the best parent was and the probability of the most likely path to the state at that time. And then do the same thing at the next time instant and the next time instant and keep going forward until you ended up with the final time instant where you could find the most likely state overall. That is basically the state with the most likely path to it. So, and then from that state, on the most likely path to that state, you know the parents. And so you could track the parents back all the way to the beginning of time to find out the most likely state sequence for the given observation sequence. This was the Viterbi algorithm. And so this also solved the problem of finding out the most likely state sequence for any observation sequence. So given this, now here's a zeroth poll. We don't have actual online polls because this is an off class of the regular scheduled class, but I'm going to just ask you these questions. So here was the poll. Viterbi search relies on the fact that the best path to a given state is an extension of the best path to one of the states in the previous time. True or false? True or false, guys? Okay. And permissible paths are ones formed by edges on the trellis. True or false? True or false? Folks? Okay, why don't you show me with a thumbs up for subsequent polls, right? When I ask you a question. Okay. So that's just a quick recap of everything we did in the past lecture. Now let's look at the main problem that we're going to address in today's class. We've already shown that we can compute the probability of an observation and the best state sequence given an observation using the HMM's parameters. But where do the HMM's parameters themselves come from? These must be learned from a collection of observation sequences. So, by the way, so here both answers are true, right? Now, so what are the HMM parameters again? Just to remind you, the HMM parameters are the matrix of transition probabilities, the initial state probability of beginning at any state Si, and the parameters of the state output distributions, which could be histograms, Gaussians, Gaussian mixtures, what have you. If you assume that they're Gaussian, then the parameters are the mean and the variance of the Gaussians associated with each state. So, which one? We're just asking about the trellis over here. Permissible paths are just the ones that are formed are the ones that are formed by edges on the trellis. So the trellis represents the edges on the trellis that represent all valid state transitions over here. So, okay. So these are the parameters we must estimate, right? Let's see how we can do this. Let's consider a very simple counting-based procedure. Let's say you're given a set of training instances and you know the exact state sequence that the process followed in generating each observation sequence in your training set. So in this case, how would we estimate HMM parameters? So I'm going to do this explanation by example in the next few slides, and then I'll show you the formula. For my example, I have a simple two-state HMM with a Gaussian PDF observation probability each of the states. And I'm going to assume that we have 3 observation sequences. And we're going to see how I can use counting to estimate all the HMM parameters. So let's say I have this 2-state HMM, the red state and the blue state, right? S1 and S2. And these are the permitted transitions. From S1, you can go back to S1 or go to S2. From S2, you can go back to S2 or go to S1. And each of the states has a Gaussian probability distribution associated with it. Now, let me assume that I have these 3 state sequences, XA1, XA2, all the way through XA10. That's my first. So these 3 training sequences. So XA1 through XA10 represents the first training sequence. XB1 through XB10 represents the second training sequence. XC1 through XC8 represents the third training sequence. And now for, just in a hypothetical situation, let's say you somehow know the exact state sequence that the system followed, the process followed in generating the observations. So for example, let's say we know that in generating the observation sequence XA1 through XA10, the process went to S1, returned to S1, went to S2, returned to S2, returned to S2, then transition to S1, return to S1, transition to S2, transition to S1, return to S1. So similarly, let's just assume that you know the exact state sequence followed by the process in generating the observation sequence. So is this observation, is this assumption make clear to you guys? What I'm assuming over here? Yes, no. What about the rest of you? Is this assumption clear, guys? Winter, Tony, Rebecca. Is this assumption clear? Mel? Anybody else? Okay, where did I lose you? Okay, I'm assuming over here that I know the state sequence that the system followed, the process followed in generating any observation sequence. That's all I'm assuming. So did that make sense? Again, the assumption here is that, remember, when I spoke of an HMM generating an observation sequence, we said the HMM goes through some state sequence and generates an observation from each state. In the actual model, you only get to see the observations. But I'm assuming for now that somehow some oracle has also given you this thing on top. And so for each of your observation sequences, you know the actual state sequence followed in generating the observation sequence. Okay? I'm just assuming that. So is that assumption clear? Because I'm going to use it. Okay. Right? So given this now, if I had to tell you what is your best guess for the initial state probabilities for HMM. Now let's look at the first time instant. In the 3 observation sequences that I've got, in the very first time instant, in 2 of these observations, it was an S1. In 1 of the observations, it was an S2. So given this, if I asked you, what is your best guess? What is your best estimate for the probability that the system will be in state S1 at the first time instant? What would you tell me? Given this 2/3, right? And S2 is going to be 1/3. It's just counting, straightforward, right? And so we know how to compute the initial state probabilities. Now, similarly, let's look at all the times where the state S1 occurs in non-terminal position. So the dark blue ellipses. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instances where the state S1 occurs in non-terminal positions. I'm speaking of non-terminal positions because I'm really speaking of, I'm going to use this for estimating transition probabilities. So these two S1s were occurred with at the final observation of a sequence. So there's no way of knowing where the process transited subsequently, so we won't use those for now. So there are 11 instances over here, 11 time instance where the system was in state S1 and there was a following state. Then in 11 of these non-terminal locations, 6 of them were followed by S1, right? So given this, if I asked you this question, if I am currently in state S1, what is the probability that I will be in S1 at the next time instant also? What would your answer be? Six over 11? Does everybody agree? Right. And what is the probability that I'm going to be in state S2 at the next time instant? 5 over 11, because there are 5 instances of S2 where the next state was of S1, where the next state was S2. And so this gives me my transition probability for from S1 to S1 is 6 over 11. My transition probability from S1 to S2 is 5 over 11. Did this make sense, guys? Yes or no? What about the rest of you? Shijyan? What about you, Satvik? This makes sense. Okay. Same thing. There are 13 non-terminal instances of S2, right? And so, of these 13 instances, 5 times, on 5 occasions, S2 is followed by S1. What is your best estimate for the probability of transitioning to S1 from S2? Anyone? What is your best estimate for the transition probability that you will transit here? So that's 5 on 13, right? 5 on 13, right? Okay. And what is your best estimate that if you're in S2, you will remain in S2? Eight and 13, because there are there were 13 instances of S2. On 5 occasions, S2 was followed by S1. On 8 occasions, S2 was followed by S2. And so I can write down the transition probabilities. The probability of transitioning from S2 to S1 is 5 on 13. The probability of transitioning from S2 to S2 is 8 on 13, right? So does that make sense to everybody? Just give me a thumbs up if it did. I see 1 thumbs up. Could I see more, please? Because I'm just going to use this. All right. Okay, thank you. Okay, Yunta, we'll get to that, right? Thank you for that question. And so here are the transition probabilities that we've learned for and the initial state probabilities that we've learned for the HMD. Right? Now, what about the observation state probabilities? Look, there are 13 instances of S1. We are now not looking at merely non-terminal instances of S1, or we are looking at all instances of S1. And so S1 has occurred 13 times. Corresponding to these 13 instances of S1 are 13 observations, right? So I can segregate these 13 observations of S1. And if I assume that my state output distribution for the state is Gaussian, from these 13 observations, I can, now this is the formula for the Gaussian on the top. The parameters are the mean and the variance, right? And so I can compute the mean of these 13 observations, and that's going to give me the mean of this Gaussian. I can compute the variance matrix, the covariance matrix of these 13 observation vectors, and that's going to give me the covariance matrix of this Gaussian. Similarly, there are now 14 observations of S2, which I have highlighted in purple, right? And correspondingly, there are 14 observation vectors. So I could segregate those out, and their mean and their variance are going to give me the parameters of the Gaussian for state S2, Gaussian state output distribution for state S2. And so using those, I can also compute the parameters of the state output distributions for each of the states. Did this make sense? Yes or no? What about the rest of you? Just give me a thumbs up if it makes sense, guys. Please respond. Otherwise, I'm going to assume I lost you. So what about the rest of you? Did this make sense? Rebecca? Shujan? Aman? Did this make sense? I seem to have lost some of you guys. Satwik? Did this make sense? Yes or no? I have 3 people. Okay. So please respond, folks. I'm going to wait for you, right? So this was assuming, okay. Now we saw how this computation was done. I'm going to try to write formulae for it. Okay. What kind of formula can I write? So the estimate formula for the initial state distribution for any state is going to be this ratio. The numerator is going over all the observation sequence. This delta over here is a Kronecker delta. Delta t equals 1 Si takes the value 1 if the state at the first time instant is Si and 0 otherwise. I sum this over all the observation sequences, and this should give me the number of observation sequences where the initial state was Si. I divide that by the number of observation sequences itself, and that should give me the estimate for the initial state probability for state Si. So is this notation making sense? This delta-based notation. Guidance? Okay, right. I'll wait for 4 or 5 yeses, right? What about the rest of you? Okay, Jayang, is this making sense? This delta-based notation. Okay, so now I can use the same delta-based notation for the rest of the terms, right? So the probability of transitioning from state Si to state Sj. This denominator, let's look at the denominator. And summing over all observation sequences. Over all observation sequences, I'm summing over all, you can see I'm going from t equals 1 to t minus 1 over all non-terminal states, non-terminal observations. And there, the term I'm summing is this one over here, this delta, which takes the value 1 if the state at time t is Si and 0 otherwise. So what is this denominator computing? Anybody? What is the denominator computing? Can anyone tell me? So, yep, at non-terminal locations, you're summing over all observation sequences, where all observation sequences are going across time, and any time until the penultimate observation. And any time you actually see the state SI, you add a 1, otherwise you don't add a 0, right? So eventually this is going to give you how many times you were in state SI. This numerator is, I do the same thing, except that this delta counts, takes the value 1 if at any time you've gone from state SI to state SJ, and 0 otherwise. So what is this numerator counting? Anyone? What's the numerator counting? Can anyone tell me this? The number of times you're transitioning from state SI to state SJ, right? So also, yes, for non-terminal states. And so now let's look at this term over here. This is the update formula for the means. The denominator, again, is simply counting the number of times the state SI happened. In the numerator, I'm summing over all observation sequences. I'm summing over all time instants. And at each time instant, I'm adding the observation if the state at the time was SI. So this delta S takes the value 1 if the state at time t is SI and 0 otherwise. So it's only adding up all the observations for which the underlying state was SI. And so the numerator is summing all observations for state SI. The denominator is summing the number of times state SI happened. And so this is going to give me the mean of all observations that were generated from state SI. The variance again, I'm going over all observations. And if the state for the observation was SI, then I'm adding this centered outer product of the vectors. So this gives me the formula for the variance. So did these two formulae make sense to you guys? Can you relate them to what's happening here? They make sense, guys. Right. So it's easy. Basically, I just rewrote them, and this Kronecker delta is being used as a selector function. You select an observation if the corresponding underlying state is state SI. And so if the state sequences are known, we can estimate all model parameters. But in general, you only have the observation sequences, not the state sequences. So what can we do given this? Any answers, guys? I don't have the state sequences, but if I did, I could estimate all the model parameters. So yeah, that's one answer. Anything else? What would you do if you were in this situation? Using only the things that you have learned so far. Here's what I can do. I can estimate the state sequence, can I not? Yes or no? Does that make sense? So we know how to estimate the state sequence, correct? We can use, what was the algorithm for estimating the state sequence? The Viterbi state alignment, right? And so this is what we can do. I can initialize my HMM parameters, then compute the state sequence, the state segmentation, and then estimate all of my probabilities. So I'm going to be using these formulae as before, except this is how I do it. I'd initialize the models. From these, I'd estimate the state sequences. And if states, and using the estimated state sequence, I can estimate all my model parameters. And if the model has not converged, I'm going to use the updated model to go back and re-estimate my state sequences. Use the re-estimated state sequence to update my model parameters and keep looping this till the parameters don't change very much anymore. This method is also called segmental k-means, and this is a very nice way of learning HMM parameters. So this makes sense to everybody? Yes or no? Yes, okay. So, okay, here's a poll. Now observe how this works. This actually ends up being a likelihood maximization procedure. When you're performing state, when you're estimating the state sequences, you're picking the most likely state sequence. So the likelihood goes up because you're always picking the most likely state sequence. Then given the state sequence, the counting-based procedure is actually a maximum likelihood procedure. So you're picking the most likely model parameters. And so here's what you're doing. From the state sequence, you're picking the most likely model parameters. From the model parameters, you're picking the most likely state sequence. So at each step, you're increasing the likelihood. And so this whole thing is a maximum likelihood procedure. That makes sense? Right. And of course, it depends on, so you're going to start out with some initial models and go through this process. So here are a couple of questions. Do you think the initialization affects the result of the parameter estimation? Meaning, can you start regardless of how you initialize the model? Will you end up at the same point? So how many of you think true? How many think false? I'd like to see a thumbs up for true. May I see a thumbs up for true? I'm not seeing any responses. Can you guys just show me a thumb? Okay, how many think false? How many of you think this is false? Okay. We'll hold on to that for a second. We need to use the observed state sequence to infer both the transition probabilities and the state output probabilities, true or false, the second poll. This is just the estimation, right? The first one is clearly false, right? Because you're committing to a state sequence. If your initial models are very poor, then your initial guess for a state sequence can be really bad. And then subsequently, the model is just going to go into a bad place. So this process is very simple. Works very nicely if you have enough training data and compute. But if you don't have sufficient training data and don't have sufficient compute, then it can end up in a bad place, right? So those of you who said false for the first one, you're right. Now, so one way, and the problem here is that you are committing to a state sequence, right? You're saying, this is what I think the state sequence was. But ideally, you don't want to make that commitment because your initial estimate might just be wrong, right? And so to change that, you want to use the expectation maximization algorithm. Instead of saying, I'm going to just choose the best state sequence, use that to estimate my model parameters, you say, I'm going to consider all possible state sequences where every observation where you consider every state sequence that is permitted by my model topology, but with a probability. And so in this process, every observation is going to contribute to every state. To see how this works, let's go back to this formula, right? What was the key component of this formula? There was a selector, this delta over here, which took the value 1 if the state at time t was Si, or the one here, which took the value 1 if the state at time t was Si and the state at time t plus 1 was Sj, right? So in general, any counting-based estimate can be written in this form with this delta. If the if you assume that you know the underlying hidden variable, right? But if you want to translate from this to the EM-based solution, there's a very simple trick. You first write your formula in terms of these deltas, and then replace all of these deltas with the posterior probabilities instead. So instead of saying, I'm going to count a 1 if the state at time t is Si, I'll replace that as what is the probability that the state at time 1 was Si. So delta t equals 1 Si simply becomes the posterior probability that the process was in state Si at time t1, time 1, given the observation sequence. So the same thing with this delta, right? These deltas are going to all become, this one is going to be, what is the posterior probability that the process was in state Si at time t, given the observation. So I just replace delta t Si by P of Si at time t, given the observation. And this one here, I'm going to replace this by the posterior probability that the state at time t was Si, the state at time t plus 1 was Sj, given the observation sequence. So did you guys understand how we went from the deltas to these posterior probabilities? The delta is a commitment. The posterior probability is hedging bets. Does this transition make sense from the previous slide to this one? I see one yes. What about the rest of you guys? Give me a thumbs up if it made sense. Okay. The delta basically says, so when we did that, so when I'm using a delta, basically I'm assuming this situation, right? That I know the state for every observation. Whereas in reality, I don't, correct? That answer your question? So instead of committing, I'm just going to replace the delta by a, and immediately this counting-based solution actually. So here's a poll. Answer to the first question. The update at each iteration is actually the EM algorithm. And the probability for every state is based on all the observation data. Does that make sense? Yeah, so true or false? Okay. And in my example, I'm assuming Gaussian distributions for the state output distributions. But the output probability does not have to be modeled by Gaussian distributions. It could be pretty much anything. So long as you can write a so long as you can write a counting-based formula, you just replace the indicator function for the counting by the posterior probability, and it all works out, right? So lovely. Both of these are true. But then the challenge is, how do I compute these posterior probabilities? And it turns out we already know this. We've done this. I've done most of the computation for this already. So the posterior probability that the state at time t, given the observation sequence, which is basically what, so if you look at these guys, forget this one on top in the second yellow. But if you look at this term here, or this term here, or the denominator term here, or these posterior probabilities, they all have the form. What is the posterior probability that the process will be in state Si at time t given the observation? For the initial state probabilities that you're specifically considering time t equals 1, but this is just one instance of these other guys, right? So let's see how we compute that. What is the probability that this process will be in state S at time t given the observation sequence? Now this is proportional to the probability that this process will be in state S at time t and generate the observation sequence. So P of S given x's is proportional to P of S and x's because of Bayes' rule, right? P of S comma x divided by P of x is going to give you P of S given x. So this means that I only need to be able to compute this probability to the right, the one here, which is the probability that the process is in state Si at time t and generates the observation sequence. So this is the probability that the process visited state Si at time t while producing the entire observation sequence, right? So what is that? If I go back and look at the trellis, the probability that this process visits some state S at time t and generates the observation sequence is the total probability of all paths through the trellis. No, it's this guy here. It's the total probability of all paths through the trellis that go through state S at time t. So it has everything into here and also everything going out. These are all the paths that go through state S at time t. Right? This making sense? The rest of you, does this make sense? Easy, right? And so this is the probability we need to compute. Well, how do we do that? It's easy. I can draw that portion of the trellis like so. All the red arrows show all the paths leading into the state. The blue arrows show all the paths going out of the state, right? And so the total probability of this colored subgraph is going to be the probability of the red portion of the graph times the probability of the blue portion of the graph, because both portions meet at Si. So here there's only one node. So I can decompose the probability as the product of the probability of the red graph, including this node, and the probability of the blue graph, not including the node. That makes sense? Yes or no? Right? So it's the probability of this portion of the graph. And what was this one? The probability of the portion of the graph ending at this node. Have we seen? This was just the alpha, right? Alpha ending over here. You guys remember this? Yes or no? Yeah. Okay, right? So the question is, what is the probability of this portion of the trellis? Now for this, we can compute this much like we computed the alphas. This is the probability that the process generates all future observations given that it is in state S at time t. So this is the beta, I'm going to call it beta. So beta ST is, beta term associated with this is the probability of generating all observations from time t plus 1, given that the process is currently in state S at time t, right? And so this is easily enough computed. What is the probability of all future observations given that it's in state S at time t? There are only three ways of generating the rest of the sequence, because this node has only 3 children. So I'd have to sum over all of the children, and what I would sum is the probability of transitioning to the child times the probability of generating. Because remember, the betas are actually not considering the node itself. So the probability of transitioning to the child times the probability of the child itself, which is, the probability of generating the t+1th observation from the child, times the probability of the entire subgraph that follows that child, which is simply going to be the beta at that node. And so beta st is the sum over all children of the probability of transitioning to the child times the probability of generating the t+1th observation from the child times the beta of the child. So this gives me a recursive formula for the betas. Does this make sense? The rest of you, that makes sense? Perfect, right? And so I can just say that at the final time instant, there is no future. So the probability of the future is 1, 1. And so I can say beta s of t equals 1 at the final time instant. And then I can begin, because the beta at each time is computed based on the betas in the future, I can start at the final time instant and work my way backwards and compute the betas for all the nodes in the trellis. And so this is just like the forward algorithm. And so I can use the forward algorithm to compute all the alphas going forward, the backward algorithm for all the alphas going backward, betas going backward, and the product of the alpha and the beta at any node is the total probability of all paths through the trellis that go through that node. So does this make sense? Rest of you guys, is that making sense? Okay. And so now, answer me this. Do we need to calculate the probability of each state and the transition probabilities between states given the observation at each update? I don't know what the question is. Let's skip this, right? But anyways. So here, what happened here was this computes the joint probability of the observation sequence and the state, right? What we need is the posterior probability of the state given the observation sequence. How would you derive that from this guy here? Anyone? How would you derive that? There's a product rule. So the probability of the state given the observation is going to be the probability of the state and the observation sequence divided by the sum over all states of the joint probability of the state and the observation sequence, which is simply alpha times beta divided by the sum over all s prime of alpha times beta. Does this make sense? Right? Easy. And so I have computed these terms and the terms in the denominator as well. And those can just be plugged into this formula, right? But I still have this one term, which is the probability of posterior probability that I went from state G at state I at time t to state G at time t+1, given the observation sequence. How do I compute that? That's proportional to the probability of being in state t at state s at time t and going to s prime at time t+1 and the entire observation sequence. That's basically the probability of this portion of the trellis. How would you compute this? Anyone? How could this be computed? Using all the terms we've seen so far. Can someone take a guess? Okay. If you were to decompose this graph, how would you decompose it? Come on, guys. Alpha, beta s prime, kind of. I can take alpha st, right? but then I have to go from ST to S prime. So I have to go from S to S prime. So times the probability of transitioning from S to S prime. And then you have to consider the observation at t plus 1 times the probability of the observation at t plus 1 from S prime times beta S prime. So does this make sense? Right? Easy once you draw the picture. And so the posterior probability, of course, is to compute the posterior probability, you'd have to sum this guy over all SS prime pairs and stick that into the denominator. As it turns out, this is the same as just the denominator here is the same as the denominator here. And this denominator is going to be the same at every time instant. So if you compute this once, then you can just plug that in here. So because this is just the probability of the entire observation sequence. And so now we know how to compute this term as well. And so we have the complete set of update rules for all of the model parameters. That makes sense? Yeah, and so this is easy, right? We know how to do it. So now our training process is going to be simple. You'd initialize all the model parameters, and using the initial model parameters, you'd compute all of these posteriors using the forward and backward algorithms, and then use the posteriors to re-estimate model parameters. So can we check this poll? It's simple. The forward-backward update rules are identical to Viterbi training update rules, with the indicator functions replaced by posterior probabilities, true or false. And now the update formulae for the state transition probabilities can be computed from alpha and beta values, but do not need to reference observations again. Would this be true? For this, you'd have to go back to this formula, and you can see that just having alphas and betas is not sufficient. At this time instant, you also need the observation probability, right? This guy. So the second one is false. And the third one, the specific parameter update rules will depend on the model. We assume Gaussians, you could use GMMs, but the general principle still remains. And so here's how the training works. This is called Baumwell's training. You'd initialize your models, you compute your posterior probabilities, update your models, and keep repeating this process till the model converges. And in practice, the segmentation-based method, the Viterbi training, is much faster, easier to implement, and is faster. But it tends to be less. It tends to run into poor local minima unless you have a large amount of training data. If you do not have enough training data, you want to use the soft association technique. So we've covered all the major HMM issues: how to find the best state sequence, how to learn HMM parameters, and how to compute the probability of an observation sequence. There are some magic numbers, how many states does the HMM should you use to model the HMM? There's no automatic technique for this. So you got to choose something. For processes like speech, the HMM topology chosen is usually left to right, no backward transitions. For other processes, the topology must reflect the nature of the process. The number of states, again, I'm using speech as an example because here some things are very clear. Like in speech, when I'm speaking of a phoneme, there's an onset of the phoneme, there's the steady state, and there's the offset. So there are 3 states. But if I'm modeling something more complex, like our kidnapping problem, you'd need more states, right? And of course, HMMs are used everywhere to model time series, for Bayesian classification, and problems relating from speech recognition, vision, gene sequencing, text mining. It's used very extensively in modeling the stock market and stock prediction and so on, where your observation sequences would be the stock values. So, and Yeah, bunch of different applications. So I'll stop right here. The reason I wanted to get through all of this is that I'm going to be building on the HMM concepts when we speak about our next topic, which is Kalman filtering. So I'll stop here. And if you have any questions, I'll take questions. Otherwise, thank you for being here this time. Any questions? All right, folks. Thank you very much. I appreciate your being here. And particularly Masa, thank you for being up at 3 in the morning.